Hello students, today I will take some examples of the simple harmonic motion. I have told you all the energy and the conservation of energy also. So I will take the examples of simple harmonic motion. Examples of SHM. Now first example is the simple pendulum. First is simple pendulum. It is an arrangement in which a heavy body is tied at one end of massless string whose other end is tied to a suspension point. It is an element in which a heavy body is tied at one end of the massless string whose other end is tied to a suspension point, so that body oscillates freely in vertical plane. So this heavy body is called the bow. The heavy body is called bow. When bow is slightly displaced from its mean position, and left to oscillate, it executes as such. The heavy body is called bow. When bow is slightly displaced from the mean position and left to oscillate, it executes as such. So now we think that let L is the effective length So this is the actual length of a string plus radius of bob. So this L equal to N plus R. And let M equal to mass of bob. And this is like this. This is the support. Here is, this is the bob. This is the suspension point S. This is the main position. Now suppose the bob is taken to this point. And let this angle is theta. Then it is released so that it goes like this. And then also it goes on this side. On this side. So this goes in this way and then goes in this side and then comes back and then goes to on this side. So thus this vibrates to and fro about this mean position. And let at any time this is in this position. This is the new position, and it has the mass, the weight mg, and it has the tension T. And if we increase to this one, then this will be the angle theta, as we have taken it to be theta. Then this we can have, this is now your mg cos theta, and one force will act in this direction, F, that is equal to mg sin theta. So let angular displacement theta equal to angular displacement. Now two forces act on the pendulum. Forces acting on the pendulum. Number one, weight mg, vertically downward, and now second is tension T in a string. So now this the weight mg can have two components. One is mg cos theta and mg sin theta. The mg cos theta is balanced by the tension in the string. In equilibrium, T equal to mg cos theta. Because this T is working towards the support, tension always acts towards the center or the point of suspension. The resultant force is only mg cos theta. Resultant force F equal to mg sin theta with a minus sign. Minus sign is because this force is always directed towards the mean position O. Whether this goes from this O to in this position A, or A to O, or O to B, or B to O. Whatever it has the moving from O to B or O to A, this F will always be directed towards the this mean position. So now we can have that this F equal to minus mg, and theta is being very small, we can take it theta, since theta is very small, so sin theta equal to theta. This we can assume. This is now force F, and now this F can have F equal to minus mg, and theta, that we can take it to be now, because these two sides are equal and this is also, so we can have let this displacement is x, displacement x, so this is equal to x upon L, theta equal to x upon L. This we take here. So now we have this F equal to minus mg L into x, but we know that F equal to minus kx. This is number 1, this is number 2. Now we compare. Comparing 1 and 2, this k equal to mg upon L, and k we know that k equal to m omega square. This is known to us. So this m will cancel. So omega equal to square root of g upon n. Omega equal to 2 pi upon t, square root of g upon n. So t equal to 2 pi square root L upon g. This is the formula for the time period of the simple pendulum. Formula for time period simple pendulum. Simple pendulum. And now you can see that this time period T depends upon dependence of time period T. Number 1, time period does not depend upon mass and mass of bob and amplitude. Because amplitude is not coming in this expression, amplitude A, the mass of the bob is also not coming here, so whether we take a heavy particle or the light particle, time period will be the same. And also if we change or increase or decrease the amplitude, then there will be no change in the time period. Also this T is independent of displacement. Amplitude and displacement. So these are three things on which this T is independent. Second, time period is proportional to square root of effective length. That means this T is proportional to square root of L. So what we have, that if suppose we are having this T and this is now square root of L, then we will get a straight line, T proportional to square root of L. And now if we suppose take a graph between T and L, then this will be like this, parabolic. It is parabolic. It is a straight line and this is parabolic. So this will go in this way. So if the effective length is increased or decreased, then time period will increase or decrease. If L increases, T will increase. If L decreases, then T will decrease. It's a very simple examples can be seen, that if suppose we are having a hollow pendulum filled with the water having a boat at the bottom, when the water is allowed to flow and the pendulum is vibrating, at that time first this the time period will go on decreasing, because as the water goes out of the bow, the effective length will increase. So time period will increase. It means that this will vibrate slowly. Similarly, if suppose a girl is swinging and suddenly he stands up, then the time period will decrease. So this means that because the center of gravity will rise up, because of that the effective length will decrease, so the time period will decrease. It means that this will vibrate with more frequency, thus the frequency increases. And now we will have the second factor. Time period depends upon gravitational acceleration. So we can have this T is proportional to 1 upon square root of G. Now value of G is different at the different places. So when the effective value of G is 0, then T is infinite. So when we go at the heights, at the altitudes, then G decreases, so time increases. So time increase means that the clock will be slow, and when we go in the space and we are falling freely, then effective value of G is 0. So the time period is infinity. It means that there is no vibrations at all. Similarly, if we go at the center of the earth, then this time period will be infinite because at the center G equal to 0. So this will be equal to infinite, and the clock will not work at the center of the earth. Similarly, if we are going at the moon, then at the moon the value of G is 1 by 6, so T will increase. So T increase means the clock will be slow. So whenever the body is falling freely, or we are at the center, or we are at the altitude, then T changes. Similarly, if suppose Bob is suspended in a moving train, in an accelerated train, even we will have this. So if we take this T here and the square root of G here, then we get a line like this. T is proportional to 1 upon square root of G. At center of earth, G equal to 0, therefore T equal to infinity. So clock stops. And for freely falling, G equal to 0, so T is equal to infinity, no reading at all. And also at altitudes, G decreases, so clocks become slow. In an accelerated train, effective value of acceleration is equal to square root of g square plus e square. This is like this, that this is now train. This is moving here with the acceleration a, and g is working in this way. Then the effective value of g will like in this way. This will be the square root of a square plus g square. This will be square root a square plus g square. So now we will have that the time period t equal to 2 pi square root of L upon g square plus a square whole raised to power 1 by 2. This is the new acceleration. So when we suspend this pendulum in a accelerated train, then t will decrease. It means that the clock will be slow. In accelerated train, t decreases and the clock will slow down. So these are the different cases in which the value of g depends. So this is about the simple pendulum. There are so many. Initially the clocks were made on the basis of simple pendulum. Now question arises that when clock is not working in the space, or when we are going in a satellite, then which clock will act there? And nowadays we are having the electronic clocks also. And the electronic clocks are not based upon this simple pendulum. They are simply the vibrations of the atoms. So the time taken by the electronic clocks is more accurate. So they are taken into the space. This is what about the simple pendulum. So you all like, share and subscribe this video and read it, because there are number of questions which are asked in the competitive exams. Your NEET and the engineering and other so many exams. So you please go through it and also share to your friends. So you all like, share and subscribe the video. Thank you.